In this lesson, we're going to review factoring strategies. We'll start by factoring out a greatest common factor, and then we will learn about factoring the difference of squares. Some of this lesson will be a review from Algebra 1. So we have a question. What comes to mind when you hear the word factor? And if you would please write your response in the blanks area. Before we factor, we actually want to remember how to multiply expressions. And so to multiply this expression, 7a times this binomial, we're going to remember that we distribute the 7a and multiply it by the 4b and then multiply it by the negative a. So 7a times 4b is 28ab. 7a times a is 7a squared. And notice I kept my minus. So my final answer is going to look like this: 28ab minus 7a squared. Okay, I'm going to do the same thing over here. I'm going to notice that the 5k is outside of the parentheses, so I'm going to distribute it to both terms. And when I do, I'm left with 20jk plus 5k. All right, so that's just a review of multiplication. When we factor, it's like the opposite of multiplying. And so in this example, we're asked to factor each expression completely. Well, these were the answers from the previous page, right? So what we want in factored form, we want at least one set of parentheses because we're going to show multiplication. So what I would do first is I would look at the two terms, and I'm going to highlight the terms that are common to both. So there's an a that's common to both. And then there's also a factor of 7 that's common to both. So if I said, what factor is common to both terms, there would be a 7 and an a that's common to both terms. And then I want to think 7a times what is 28ab. So we're kind of doing a type of division, right? 7a times 4b will give me that original term of 28ab. 7a times what is 7a squared? 7a times 1a. I also could have just written this without the 1 as the coefficient of a. These are equivalent. So I have factored the given binomial by factoring out the greatest common factor. And the greatest common factor between the two terms was 7a. It was something I could divide both terms by. So now we're going to look over here. And the same thing, we want to find out what is the greatest common factor between 5 and 20. I usually start with my numbers. I know 5 is the biggest number. I can divide them both by. And then I would look at the variables. They both have a k. And now I would use my parentheses. 5k times what is 20jk? That would be 4j. 5k times what is 5k? A lot of students forget to complete it with the plus 1. So let's highlight that so you don't forget. It's really important that you include that plus 1 or sometimes a minus 1. That's the factored form. So now we have a couple more examples. And if you feel like you can continue without listening to the instruction, you'd go for it and then just check back and make sure you got it. I'm looking at these numbers and I know that 15 and 30, I know that the greatest common factor that they have is 15. I can see that each of the two terms have an x and each of the two terms have a y. And now I think 15xy times what is 30? X squared y. So it has to be 2x. And here's where I need to remember that 1. 15xy times 1 is 15xy. Well, look over here, and we're going to notice right away that both terms are negative. So when both terms are negative, it's a really good idea to factor out the negative. 5 is the greatest common factor between 5 and 35. Don't forget the x. Negative 5x squared, how do I get there? Well, I'm going to do negative 5x times x, right? Negative 5x times what is negative 35xy squared? Well, negative 5 times positive 7. The x is already accounted for. I just need to include my y squared. So this is my factored form for the second example. Okay, so that was a review of factoring out the greatest common factor, but there's a second topic in this lesson, and it is factoring a binomial into the difference using the difference of perfect squares. Okay, so that sounds rather daunting, but what I want to do is just start by a simple multiplication exercise. Remember, to multiply binomials, what we would do is we would write the first binomial factor up top. We would write the second binomial factor along the side. And then what we would do is we would multiply the two parts together and write the product in here. So for example, 5x times 5x is 25x squared. Remembering this process, I hope. 5x times negative 3 is negative 15x. 5x times positive 3 is positive 15x. You can put the plus sign down or leave it out. 3 times negative 3 is negative 9. Okay, and this is where we want to combine any like terms that we have. So I will highlight the like terms that I see. These are my linear terms. They're the x terms. They're like terms, so I can add them together, but they're opposites, so they will actually cancel out. So my final product that results in the multiplication of these two binomials is 25x squared minus 9. Okay. Now we'll look at the next example. And we have x to the third this time, plus 7. X to the third minus 7. And what we want to do is we want to multiply and put our different terms inside this box. So x cubed times x cubed, well, let's think about that. There's going to be 6 x's being multiplied together, right? So this is going to be x to the 6th. 7 times x cubed is 7x cubed. Negative 7 times x cubed is negative 7x cubed. And 7 times negative 7 is negative 49. Okay, so once again, we are going to look for like terms, and we notice them along the diagonal. These cubic terms are going to actually cancel out. And so my answer to this problem, this product, when I multiply these two together, is going to be x to the 6th minus 49. Okay, so this is where I always ask students to stop and pause and notice something interesting about the examples. So I hope that somebody noticed that you are multiplying in essence, the same binomial, right? They're identical, except one has a minus and one has a plus. The same binomial, right? One has a plus, one has a minus. So when that is true, the middle terms will always cancel out, leaving you with a binomial that will always have a minus sign. So it's going to be the difference of, and what you're subtracting will always be perfect squares. So 25, x squared is a perfect square, 9 is a perfect square. X to the 6th is a perfect square because it's x cubed times x cubed. 49 is a perfect square. So we call these expressions the difference of perfect squares. And what we want to do is we want to be so observant in that we know immediately how to factor it. We're going to factor these into the product of two binomials. Take a look now. Let's really break this down so that there's no mystery in this. And so the square root of the first term goes in the first slot. You see that? The square root of the second term, -9, goes in the second slot. So this is how we factor the difference of perfect squares. And we will always have a plus, a minus, and a plus, or a plus and a minus. So that's how we're going to factor the difference of perfect squares. So once again, the difference of perfect squares, I have my minus sign, I have a perfect square and a perfect square. So I'm going to factor this expression into the product of two binomials, where the first term in each is the square root of a squared. The second term is the square root of b squared. And then I need, as signs, a plus and a minus, or a minus and a plus, does not matter the order, but I need those signs to be different. So that's the general form to factor the difference of perfect squares. So then we'll look at the next example. And this next example is very tricky for students. Students want to do this. They want to say, oh, I have a perfect square and I have a perfect square. Okay, so let me just take the square root of 25x squared. And they say 5x. And they say, let me take the square root of 49y squared, which they know is 7y. And then they say, oh, you know what? They think this is the difference of perfect squares. So I want to just multiply the same thing together. I'm going to have 1 minus and 1 plus. And sadly, they will lose credit for their work. This will be incorrect, sadly, because there's something important that they missed in this problem. They missed that this was a plus sign, and we always need a minus sign. So pay special attention to the fact that we're calling this the difference of perfect squares. So we need a minus sign and two perfect squares. All right, keeping that in mind, now I want to actually think about the phrase perfect squares. We've heard about this word since 7th grade. 8th grade, we really got thinking about them when we had to use the Pythagorean theorem. Perfect squares are so important. One example of a perfect square would be the number 25. 25 is a perfect square. And you say, well, why is that? Well, you know what? You can make a square, right? 5 by 5, where the area of that square is 25. So the area of any square with integer side length is a perfect square. Now, what's my smallest perfect square? Okay, well, that would be the number 1, because it's 1 squared. What about 2 squared? Well, that would have area 4. Square that's 3 by 3 would have area 9. 4 by 4, 16. 5 by 5 has 25. And you know these. 7 times 7 is 49. And if you don't, we're going to encourage you strongly to commit these to memory. There is just something very mathematically significant about perfect squares that we want you to recognize them. This is 11 squared, 12 squared. We would love for you to have up to 25 squared memorized, but we know that it takes time. 15 squared is 225. 16 squared is 256. Oh, now I'm testing my own memory. 17 squared is 289. 18 squared is 324. 19 squared is 361. And 20 squared is 400. Oh, yay. I still have them in my memory. Love that. So, yeah, so these are the first 20 perfect squares. And I'm just double checking that I didn't make a mistake. I had to memorize them way back in high school, and they're still in my memory. Yeah. Okay, great. So, important notation. I'm going to use my pencil tool. Let's remember that when we have a number and we have an exponent of 2, we say 6 squared. In words, we say 6 squared. And we know that that means 36. It means multiply 6 by itself. Okay, another important notation to remember is this symbol. This symbol means the square root. So if I said to you, what is the square root of 361? Well, you could use a calculator, but if you have your perfect squares memorized, you just look up at your chart, right? And you'd say, okay, if 20 squared is 400, this one must be 19 squared. So the square root of 361 is 19. All right, now let's put this into practice. I will ask you first a true-false question based on the things we've talked about already in this video. Have I factored this binomial correctly? If I have, then this statement is true. If I haven't, then this statement is false, and you're going to choose one, okay? Alrighty, now we are going to get some practice with factoring, and I'm noticing I have a perfect square. I'm going to use my highlighter. I have a perfect square number, and I have a perfect square number. And I'm going to use the other highlighter for the variables. I have a perfect square variable and another perfect square. Anytime I have an even exponent, it's a perfect square. So I definitely can write this as parenthesis, the square root of 81x squared is 9x. The square root of 196 is 14, y squared. And then I'll put a minus sign here. I'll copy this exact expression, except change this to a plus. That is how we factor a binomial as the difference of perfect squares. We factor it this way. Now we'll try the next example. And what I'm noticing is I don't have a difference of perfect squares, but I can rewrite it so it is a difference. I can put my positive term first, right? And then I can put my minus 49a squared second. And that is mathematically equivalent, right? I've just used the commutative property. And now I do have the difference of perfect squares. I know the square root of 25b squared is 5b. The square root of 49a squared is 7a. Now I want to write this same binomial just with a plus sign. How are you feeling so far about the difference of perfect squares? So you want to recognize a couple of things. Recognize that there's a binomial that is being asked to factor. There's a minus sign, and the two things that are being subtracted are both perfect squares. All right, let's take a look and see what the next example is. All right, so here are 3 examples that we would actually like you to try. And so remembering that we're talking about the difference of perfect squares, put the video on pause, try all 3. It is possible that one or more maybe can't be factored, in which case you just write prime, can't be factored. Put it on pause and then come back when you're ready. All right, so the first one, I am noticing a perfect square, yay. Another perfect square, excellent. But there's a plus sign. So this is prime. This cannot be factored. Did we trick you on that one, or did you remember you can't factor if it has a plus? All right, now we'll look at the next example. And I have a perfect square for sure, that's 17 squared. I have another perfect square, because n to the fifth times n to the fifth is n to the 10th. And the number 1 is a perfect square. Excellent. So I can factor this into 17 n to the fifth minus 1 times 17 n to the fifth plus 1. All right? The last example, let's take a look at it. Looks rather tricky at first. At first, you might think this can't be factored. But hey, look it, there's a common factor I can take out of there of 5, right? Let's factor out that 5 and see what happens next. Did you think to do that? Did you think to factor that 5 out? If so, awesome, because now look, now I do have the difference of perfect squares there. So, actually, I'll put it right next to this equal sign. I can keep my 5. I can factor the binomial into a minus b times a plus b. All right, so there's your lesson. And before we move on to other things, I want you to write down what you want to remember about factoring out a greatest common factor and factoring using the difference of two squares.